All right, welcome. We're going to talk through the 2016 problem number 3 now, which has some Unit 4 topics, but again, there's a variety of different things in here. This isn't the entire question 3, but it's a good probably half of it. And we've got this setup here. We've got a molar mass of we've got an unknown metal, M. We don't know what it is. Could be calcium, could be iron. We don't know what it is. And we're trying to figure out the molar mass of it. In order to do this, the student reacts it with iodine, and notice that, that the metal in this case is in excess. So reacts with an excess of the metal, and that tells us that the iodine is limiting, which is useful to know because the limiting reactant determines how much product is made. So since iodine is limiting, we could, if we can later on figure out how much product we made, we can figure out how much iodine there was. So keep that in mind. And we made a water-soluble compound Mi2. Maybe that'll be useful later, represented by the equation above. So we have balanced chemical equation. The reaction proceeds until all of the I2 is consumed. So again, we're emphasizing that the iodine is the limiting reactant. It all gets used up. And then they quantitatively collect the Mi2. That means they collect it in a way that we can measure it. So quantitative, we're thinking measuring something, get some accurate numbers here, and we dry it and weigh it to a constant mass. So this is similar to, well, it looks like we were kind of filtering out the leftover M. So we did a filtration in class. This one's kind of the opposite. In this case, you're filtering out the leftover M and you're wanting to just collect the solution that contains the Mi2, which it mentions is water soluble. So in this case, our product's dissolved in water. So they collect the water with the Mi2 dissolved in it and then heat it up to remove all the water to make sure you have this dry sample of Mi2. So this time we're collecting a water-soluble product. It's a little different. That's cool. And then here's our experimental steps below. And then we've got a data table. So they give you a visual to try and understand what's happening here. This might not be the type of experiment that we've done before. It's a little different. So that's why they give you this nice visual. Okay. So here's the data summarized in a table. That's also given here, which is nice. So the question is, given that metal M is in excess, calculate the number of moles of I2 that reacted. Well, we know that I2 is limiting, right? And they made it very clear that all the I2 got used up. So that means if we're trying to figure out the moles of I2 that reacted, that's going to be the same as the moles of I2 that were initially added to the beaker, because they said all of the iodine gets used up. So really we just got to figure out how much iodine we initially added to the beaker. So we've got if you look back at our data sets, it looks like this mass tells us the mass of the beaker plus metal M. This mass tells us the beaker plus M plus I2. So it looks like if we subtract these two numbers, we should be able to get the mass of just iodine by itself. So for A, first thing we're doing is we're going to do some subtracting. So this is the mass including the iodine. This is the mass not including the iodine. And if you subtract them, you get 1.021 grams of iodine. And then we want to find moles of iodine, 1.021 grams of iodine. And so we're going to use the molar mass. So 1 mole of iodine is 253.8. Keep in mind it's I2, so you remember to double the molar mass of iodine there. And then this is the type of question you could definitely get graded for sig figs on. So notice how we have 4 sig figs in our answers here. Quick review, the sig fig rules for subtracting is you look at the number of spots to the right of the decimal. So these values both go to the tens, hundreds, thousands place. So my answer will also go to the thousands place. As a result, this number has 4 sig figs. And then when you're doing a multiply divide type of calculation, then your answer will have the same number of sig figs as your value with the least sig figs. So this answer will also have 4 sig figs in it. So there we go. And then I just also want to pause and say, remember one of the goals of working through some of these AP release problems is just to work on our problem solving strategies and looking at, novel situations. This is a type of reaction that most people wouldn't have actually done in real life in a lab. It's kind of a little bit of an odd reaction, but we want to practice applying our knowledge of stoichiometry and just lab skills and kind of reading through a problem and saying, what information is it giving me? What am I trying to find? So really just working on our strengthening our problem solving skills here. Okay, so we've got our moles of iodine. Cool. And then we want to find the molar mass of the unknown metal. There's a way that it shows it in the answer key, and I actually would approach it a little bit different. So I'll show you the way I approached it. You can also look at the scoring guidelines and see what they said there. And there's always different approaches to problems. So if you look at a scoring guideline and they do it a different way than you did it, like that doesn't mean what you did was wrong, right? There's always several different approaches to solving a problem. So the way I would think of it, I'm trying to find the molar mass of M. So what I would do is I'd say, what do I know? Well, I know that I reacted 0.004023 moles of iodine. And I know that M is in excess. So what I'm going to do is I'm going to use this, since iodine's limiting, I know it's going to determine how much Mi2 I make there. So I know that this is how much iodine reacted. And I know that the mole ratio is 1 to 1. So I know for every 1 mole of iodine, I make 1 mole of Mi2. So what that means is I made 0.004023 moles of Mi2. Cool. And then I know the mass of Mi2 right there. So that's key piece of information. Maybe I should have mentioned earlier. It looks like they give us the mass of our product Mi2. And we know that the molar mass is the grams per mole. So to find the molar mass of a known substance, you just take the grams, measured grams, and divide it by your, measured number of moles. So it's going to look a little bit like this. So this is my mass of Mi2. This is my moles of Mi2. If I plug that into my calculator, I can see that my molar mass of Mi2 is 319. I don't want to stop there, though, because the question doesn't ask me what's the molar mass of Mi2. It's asking me what is the molar mass of M. Okay, so I know that Mi2, let me write this up here, Mi2 weighs 319 grams, and I'm lost track of my sig figs here, sorry. Okay, and I know that Mi2 is made of an M and 2 iodines. I know the molar mass of iodine, so iodine is 126.9. So I know that these values add up to 319. So if I do some math here, do some subtracting, I can figure out the molar mass of M is actually 66 grams per mole. I think it ends up being 65.4 if you're doing a good job with sig figs, but there we go. So this was how I approached this problem. Again, there's different approaches you could take, but okay. So this is an example, just putting this in a greater context when you're trying to identify unknowns. There's 2 main types of strategies. There's titration and there is gravimetric analysis. So in other problems, we might see titration as a way to analyze an unknown. This was an example of gravimetric analysis, meaning what we did is we collected and purified and dried and weighed a sample. In this case, we were collecting and drying and weighing the product, Mi2, and then we used that to figure out something about our unknown. In this case, we weren't trying to figure out the concentration of our unknown, we were trying to figure out the molar mass of our unknown. But it's a way for us to analyze an unknown by weighing one of the products of the reaction. So this is similar to what we did in our lab, the hard water lab, where we collected the precipitate calcium carbonate and used that to figure out how much calcium ions there were in the original solution. So a couple other questions here. The student hypothesizes that the compound is ionic. Propose a test that they could use to support this hypothesis and explain how the results would support the hypothesis if it was ionic. So here's actually, you're kind of thinking back to maybe Unit 2 with bonding, and you're thinking of the properties of ionic compounds. And one of the things that stands out with ionic compounds is that when they dissolve in water, they conduct electricity. And this could be particularly helpful because they did mention earlier that this is a water-soluble compound. So one thing you could do is you could say, I'm going to dissolve it in water and see if it conducts electricity. And that would give us an indication that it's an ionic compound. The other thing you might do, you might remember that a property of ionic compound is you could test the melting point. And if you heat it up really high, it takes a long time to melt. If it has a high melting point, that would indicate that it's likely an ionic compound. So either one of those would work. And then one more question here. This is, remember we were looking at the reaction of metal with iodine, and then the student makes a hypothesis about, well, what if it reacts with bromine? And notice that iodine is a solid at room temperature while bromine is a liquid. And so I want to explain why that is, thinking about intermolecular forces. So iodine, bromine, they're both nonmetals. They're both examples of molecular covalent substances. And molecular covalent substances are held together by IMFs. That's what I'm thinking about. What are those IMFs? You could have dispersion forces. Sometimes people call them LDF, dispersion. Those are found in all molecules. If your molecule is polar, it also experiences dipole forces. And if it has an H bonded to an N or F, it would include hydrogen bonding. So in these molecules, we have two atoms of the same thing bonded together. So they have the same electronegativity. So these atoms are both definitely nonpolar because we're bonding the same atom together. And if they're nonpolar, the only IMF they experience is dispersion. So if they have the same IMF, how come iodine, which is a solid, bromine is a liquid? If iodine is a solid and bromine is a liquid, that indicates that iodine has stronger IMFs than bromine does. So an explanation for why that is would have to do with the size of the electron cloud. So we know dispersion forces vary with size. So your iodine atoms have a larger electron cloud than your bromine. So that is going to give them, your I2 is going to have stronger dispersion forces than your bromine will. You might see the vocabulary termed polarizable thrown around. Polarizable. So if you see that thrown around, that's referring to dispersion forces. So what happens, the reason why atoms with larger electron clouds have stronger dispersion forces is because we say those electron clouds are more polarizable. And that is the kind of source of the dispersion force that is present there. All right, and I think that's it for this problem. So again, email me if you have any questions.